Greetings and welcome to my channel. I'm Mr. D, and today we're discussing how to write chemical formulas. We'll be looking at writing formulas for simple ionic compounds and some simple covalent compounds. We have a lot to cover, so let's get started. Ionic compounds, as the name suggests, are composed of ions. They'll have a positive half and a negative half. You'll sometimes see them referred to as salts. Most people will think of sodium chloride when they hear this word, but this compound is just one of a myriad of substances that scientists call salts. Specifically, we call it NaCl, table salt. Which ion will be the positive one, the metal or the nonmetal? If you said metal, you're correct. Metals lose electrons and become positively charged ions or cations. Nonmetals gain electrons to become negatively charged ions or anions. Most, but not all, polyatomic ions are anions. In the video description below, I have a link to a list of common ions that can be downloaded and printed out. I strongly suggest you memorize them, as it'll greatly speed up the process of writing formulas and naming compounds, as opposed to constantly having to look up the ions or their charges. Recall that many of the monatomic ions, single atom ions, can be determined by looking at your periodic table. So looking at our periodic table, group 1A, they have one valence electron. They have a tendency to lose that one electron. Remember, metals want to lose electrons to get the next level in, being like a noble gas configuration. So they lose that one electron, get a 1 plus charge. Group 2A has two valence electrons. So in order to get a noble gas configuration, they need to lose 2 electrons. So they take on a 2 plus charge. 3A would be 3 plus. For the nonmetals, group 7A, our halogens, which are the most active of the nonmetals, only need one more electron to get a noble gas configuration. They want that electron pretty bad, so they gain it very readily and get a 1 minus charge. Group 6A needs 2 electrons to get a noble gas configuration, so it's a 2 minus charge. And then group 5A is going to gain 3 electrons, so it'd be a 3 minus charge. Some metals, primarily transition metals, can form more than one type of ion. In the ion name, you'll see a Roman numeral in parentheses after the element's name. This number indicates the charge of the atom. Remember, these are metals, so that they'll have what kind of a charge? A positive one. Let's start our formula writing with the binary ionic compounds. Binary tells us that the compounds are composed of just 2 elements. This is where having that ion sheet handy will be of use to you. So why don't you pause here and go print that out, and I'll be here when you get back. Okay, you've got it? Good. Now let's get started. Okay, so our first example is going to be sodium chloride. So sodium is our first element. It's the metal, so it'll be the one with the positive charge. It's going to be a 1 plus. Now I'm going to write the number for the sake of clarity here, but technically speaking, you don't need to write the number for charges. If there's no number written, it's understood to be 1. Chloride is a 1 minus. Now when you're writing the formula for compounds, the point here is to try to get your charge to be 0. So 1 plus and a 1 minus, you can have a 0 charge. So it simply means you need 1 sodium and 1 chloride. So the formula for sodium chloride is simply NaCl. Our second example is going to be barium oxide. Barium has a 2 plus charge. Oxide is a 2 minus. So again, we have 2 plus and 2 minus equaling 0, so we simply need 1 barium ion and 1 oxide ion. Our next example is going to be iron 3 phosphide. iron 3 is a 3 plus charge. Remember that Roman numeral tells you the charge on the ion. This is one of our transition elements that has more than one type of charge, so we use the Roman numeral to tell you what charge it has. The phosphide ion is P3 minus. So 3 plus, 3 minus. Once again, one atom of each ion. Excuse me, one ion of each type. FeP. All right, so all these have been pretty simple so far because the charges are all equal 0 without you having to do anything. Let's look at some more that are a little more complicated now. Lithium sulfide is our next one. Lithium is a 1 plus. The sulfide ion is a 2 minus. So this time we don't have a charge of 0 right off the bat. So what we're going to have to do here is we're going to have to do its crossing. It's called crossing. We're simply going to use the same number that's in this charge as the subscript for this element, and the same number that's in this charge as the subscript for this element, this ion. Please keep in mind, we're not moving the charge, we're not moving the number, we're simply using the same one that is in the charge as the subscript for the other one. So lithium, I'm going to have two ions, and sulfur, I'm just going to have one. Sulfide, I'm just going to have one. And since there's just one, we don't put a subscript. If there's no subscript written, it's understood to be one. So this one would be Li2S for lithium sulfide. Our next example is going to be magnesium fluoride. Magnesium is Mg with a 2 plus charge. Fluoride is an F with a 1 minus charge. So I'm going to use a 2 as the subscript for the fluorine, or for the fluoride, and a 1 as my understood subscript for magnesium. So Mg F2. Aluminum oxide is our next one. So aluminum is Al 3 plus, oxide is O 2 minus. So a 3 for the subscript for the oxide, 2 as the subscript for the aluminum. So Al2O3. All right, we'll do one more before we move on. Calcium nitride. Calcium, Ca, 2 plus. Nitride is N, 3 minus. So I'm going to have a 2 as my subscript for the nitride ion, and a 3 as the subscript for the calcium ion. Remember, we're not moving the number from the charge. We're not moving the charge itself. We're simply using the same number that's in the charge as a subscript for the other ion. So Ca3N2. Now, let's look at some ionic ternary compounds. These are going to be metals bonded to polyatomic ions. As you may recall, ionic compounds are composed of a metal bonded to a nonmetal, or a metal bonded to a polyatomic ion. Poly means many, so it's a many atom ion. A polyatomic ion is one that's made up of 2 or more atoms covalently bonded together, and as a group they have a charge. An example would be the sulfate ion. Okay, so with the polyatomic ions, things are going to get a little bit hairier. Our first example is going to be a simple one. Silver nitrate. Silver Ag 1 plus. Nitrate polyatomic ion NO3 1 minus. The charges are already 0, so I don't have to do anything with any additional subscripts. So it's simply AgNO3. I'm including the subscript that's already there because that's part of the polyatomic ion, so I have to include that. So copper 2, Cu 2 plus. Remember the Roman numeral tells you what the charge is. Hydrogen phosphate is HPO4 2 minus. Again, our charges are 0. Our total charge is 0. So CuHPO4. Okay, our next example is going to be magnesium hydrogen sulfide. Magnesium is a 2 plus. Hydrogen sulfide is HS with a 1 minus charge. So I'm going to need 2 hydrogen sulfide ions and 1 magnesium ion. So 1 magnesium ion, and then for the hydrogen sulfide ion, I need 2 of them. So put the polyatomic ion in parentheses and then your subscript. Sodium, peroxide. Sodium Na 1 plus. Peroxide is a polyatomic ion O2 with a 2 minus charge. So I need 1 peroxide ion, 2 sodium ions. 2 sodium ions, and just 1 of those peroxides. Since it's, again, remember it's an understood one, so I don't have to write it. So it's not like I put parentheses around the O2 or anything. Okay? All right, let's try lithium carbonate. Lithium is a 1 plus. Carbonate ion is CO3 2 minus. So I need 1 carbonate, 2 lithiums. Ammonium nitrate. Ammonium is one of our few polyatomic ions with a positive charge. It's NH4 with a 1 plus charge. Nitrate ion is NO3 with a 1 minus charge. So this is a pretty simple one. It's simply NH4NO3. Okay, one last example. This is going to be a little complicated. We're going to be using another one of our polyatomic ions with a positive charge, and it's mercury 1. And the compound is mercury 1 iodate. Mercury 1 is Hg2 2+. I know it's got a 2+ charge there, but we have a subscript of 2 here, so that means there are 2 mercuries, each of which having a 1+ charge, and as a polyatomic ion, as 2 of those ions together, it's got a 2+ charge. But it's called mercury 1 because each of the individual mercury ions is a 1+ charge. Iodate is IO3 1-. So I need 2 iodate ions and one of the mercury 1s. So Hg2, one of those, and I'm going to need 2 IO3s. So I'm going to put the polyatomic ion in parentheses and then the subscript. Okay, that does it for ionic compounds. Next, we want to look at formulas for binary covalent compounds. These are generally going to be 2 nonmetals, but occasionally you'll see a metalloid bonded to a nonmetal. Don't let that throw you, just treat it the same way. If you looked at or printed out the ion sheet, you probably saw a list of prefixes on the next page. We're going to need those prefixes for this next section. We use the prefixes to indicate the number of atoms of each element in the compound. So you're getting the element's name and the quantities of their atoms in the compound's name. Nothing to look up, no numbers to cross, no charges to worry about. You're just doing what the name tells you. If the first element doesn't have a prefix, it's understood to be 1. So the first element gets a prefix only if there's more than 1 atom. The second element always gets a prefix. Binary covalent compounds are pretty simple because you're basically just doing what the name tells you to do. You're writing down what the name tells you. So our first example here is carbon monoxide. There's no prefix, so it's understood that it's just going to be 1 carbon. So carbon monoxide, 1 oxygen, 1 oxide. So it's simply CO. Dinitrogen tetroxide. So dinitrogen, I need 2 nitrogens, N2. Tetroxide, tetra is 4, so I need 4 oxygens, so O4. Simple as that. Sulfur trioxide. Sulfur has no prefix, so it's understood to be 1, so S. Trioxide, tri is 3, so O3, SO3. Silicon dioxide. Silicon is Si. No prefix, understood to be 1. Dioxide, O2, because the prefix di is 2. Chlorine trifluoride. No prefix for the chlorine, so understood to be 1. Trifluoride, 3 fluoride ions. And one last example, sulfur hexafluoride. No prefix, undus to be 1. Hexa is 6, so 6 fluoride ions. Okay, that does it for formula writing. In the next episode, we'll tackle going in reverse, writing the name from the given formula. Today's episode was brought to you by the element lithium. Lithium is a shiny, soft, silvery metal. Of all the metals, it's the least dense. It is one of the most active elements on the periodic table, so you'll never find it in its elemental form. It makes up only 0.002% of the Earth's crust. It was discovered in 1817 by Johann August Arfwedson. It was discovered from a mineral where the other alkali metals were isolated from plant sources. It is for this reason that its name was derived from lithos, the Greek word for stone. While Bolivia has 49% of the Earth's known reserves, it processes little if any of it. Chile and Australia are the two top producers of processed lithium. Although lithium is found in trace amounts in organisms, there are no known biological uses for it. However, lithium carbonate is a major drug used in the treatment of bipolar disorder. Several of its alloys and compounds are produced at an industrial scale. It is alloyed with magnesium for the use in armor plating and with aluminum for the use in bikes, high-speed trains, airplanes to make them stronger and more lightweight. Lithium's most important use is in rechargeable batteries in cell phones, electric vehicles, and laptops. Thank you for watching my video. I hope you found it both informative and interesting. If you did, please smash that like button below and consider subscribing and hitting the notification bell so you know when my next video comes out. When it does, please join me again. Until then, be good, be careful, and don't trust atoms. They make up things.